really important aspect of vectors, and that is that they don't have position. So I can take that vector and move it anywhere else on the piece of paper as long as I maintain its length and its direction, and it's the same vector. So that vector from A to B is the same vector if I move its tail to B. Then it'll have an arrow kind of pointing off away from B now, away from the direction to A, but it'll be the same vector. Does that all make sense? So I can move that vector anywhere on the plane, on the paper, and it's still the same vector because vectors don't have position. They just have length or magnitude and direction. And those are different things from having a position. Does that make sense? Yeah, I won't even, you don't have to answer, but do answer if it doesn't make sense. Maybe I'll put it that way. Okay, and so that's kind of all we need to know about displacement vectors and the kind of the difference between distance and so on. So I could say that the displacement from city A to city B is, say, 20 miles, 20 degrees north of east. That would represent that vector. I tell you how long it is, and I tell you what direction it is, 20 degrees north of east, and I can move it anywhere on the page and get the same thing. But now we want to talk about velocity and speed. Velocity is basically how much is the ratio of a displacement to a time. So if I go from city A, for instance, if I go, well, let's just say from those two, 20 miles, if I go from city A to city B, which is 20 miles, is that what I said? 20 miles, 20 degrees north of east. Let me just make that hit anyway. 20 miles, 20 degrees north of east. If I do that in 10 minutes, well, that would be pretty fast. Let's say I did it in an hour. If I did that in 1 hour, then my average velocity would be 20 miles per hour, 20 degrees north of east. In other words, I traveled 20 miles north of east in 1 hour. That gives me an average velocity of 20 miles north of east per hour. 20 miles per hour, 20 degrees north of east. And that would be my average velocity, even if I went along roads that actually maybe I had to cover a distance of 40 miles getting from A to B. Maybe I actually traveled a distance of 40 miles, but I only ended up 20 miles away from city A. And so my velocity was that displacement, the 20 miles divided by the 1 hour, 20 miles per hour, and the direction was 20 degrees north of east. And this is pretty typical, right? Have to travel faster on average. The actual speed that you were traveling was more than your average velocity. Okay, and so that's pretty much all we need to know. But that difference between, for instance, I might have traveled at an average speed of 40 miles per hour, very different magnitude, and it doesn't have a direction. When I say that, I'm not talking about a direction. I'm just saying how much distance did I cover over the course of an hour. But now acceleration. I just wanted to get to acceleration pretty quickly, and I think we only need a few more minutes to do this. But it is a little tricky because we have to now really understand what we mean about changing vectors. So when we accelerate, we change our velocity vector from something, some initial value, to some final value. So what I want you to do is draw a velocity vector on your piece of paper that is 30 miles per hour east, due east. So that would be, I guess, in a typical map, that would be pointing to the right on your piece of paper. 30 miles per hour. You can make it some arbitrary length. It doesn't matter. Make it an inch or two or something. Probably like something like an inch. And just call that a velocity vector of 30 miles per hour east. And then somewhere else on your piece of paper, draw another velocity vector this time 40 miles per hour north. So this vector is going to be kind of pointing probably toward the top of the page if you have a typical map in mind. 40 miles per hour is a little bigger than 30 miles per hour, so you should draw it a little bit longer. It should be about 30% longer than your first vector, and it should be pointing toward the top of the page, which we'll call north. And you could draw those two vectors anywhere you want because vectors don't have positions. They just have lengths or magnitudes, as we call them, and directions. So let's suppose now that you're traveling in your car. Your speedometer is a nice thing. It tells you how fast you're traveling, and then if you have a compass in your dash, it'll tell you what direction you're traveling. So let's suppose you are traveling in your car along a road, and maybe the road curves so that you're traveling 30 miles per hour east with that initial velocity that I mentioned. And then let's suppose that 10 seconds later, you're traveling 40 miles per hour north. So the road curved to the north and you sped up a little bit, right? You would have had to step on the accelerator pedal. And you notice that while you're turning, of course, you kind of also had a tendency to kind of be thrown outward, this centrifugal effect or whatever. We don't have to talk about that. We're just talking about kinematics here. But it's worth kind of really feeling what this also feels like. That gets to the next lesson, which is on dynamics, but we don't have to talk about that. So your car starts out traveling 30 miles per hour east, and it ends up traveling 40 miles per hour north. Now, what is the acceleration? Well, acceleration is defined as the change in velocity divided by the elapsed time. Okay, so you might write that down. Acceleration is change in velocity. You can notate that with a little Greek delta. If you know what the capital delta looks like in Greek, that's what we always use for change. Delta V divided by delta T is what I would say, the change in what time it is, which is how much time elapsed. So that's what acceleration is defined as. How do I calculate delta V, the change in a vector? And this is really the central thing to get at. So first of all, when I calculate the change in anything, I take its final value minus its initial value. That should make sense. If I calculate the change in the apples in my basket, I take the final number of apples in my basket and subtract the initial value, initial number of apples in my basket. Same with vectors. If I want to find the change in velocity, I take the final velocity and I subtract the initial velocity. That's a little weird though, because you might not, and we can do it that way. We can subtract vectors, but rather than doing it that way, I like to take that equation, delta V, it's a vector. I put a little arrow over it, frankly, to remind myself it's a vector. Delta V with a little arrow over it equals V final with a little vector over it minus V initial with a little vector over it. I can rewrite that equation as V final with a little arrow over it equals V initial with a little vector over it plus delta V. And this will be a nice way to get to how I actually find my delta V with a little vector over it. So once again, either draw your V initial or just use the one you already drew. So I start somewhere, I draw a little vector. It's got an arrowhead on it. To add a vector to a vector, I take my second vector and I start at the end, at the arrow tip of the first vector, and then I draw it from there. So draw your V initial, start somewhere, ends pointing out to the east, 30 miles per hour. Now I start at the tip of that vector and I draw another vector that will take me to a place such that if I were to draw a vector from the initial starting point, the tail of the V initial and end at that tip of that second vector, I get my final vector. Now I know what I want. I want my final vector to be 40 miles per hour pointing north. So I have to start from the tip of my V initial. I'll draw the V initial. Now I need to start at the tip of the V initial and end up at a place that represents 40 miles per hour north of my initial point. And if you do that correctly, you should draw a triangle in the following way. You draw a line representing 30 to the right, and then you draw a line that goes kind of up and to the left until you end up 40 above your initial point. You'll have a right triangle that has one side of 30, another side of 40, a right angle there, and a hypotenuse that you can calculate from Pythagorean theorem. Now, so I want to stop and just say, did I go too fast there? Just signal me if I need to go over that again. So what you should
I'm
have done is,
I'm uh,
oh yeah, go
I'm
ahead.
following
Are
you
you
with the
doing it,
drawing.
Shamash?
Oh yeah, yeah, yeah. I hope people can see it.
Let me
And
see if I can see it.
if you can click in the chat, uh, and then try to see what we have.
So what happens, this is what happened to me yesterday, Shamash. Immediately it says I have to give the meeting the use of my microphone and camera. And if
No,
I
no, no, no.
don't,
Just say no, and then say join via browser.
okay, so I have to say block, okay? And then I have to enter my name,
Just anything. Just put anything if you're not
okay?
comfortable with your name.
Okay. Ah, look at that. Okay, it actually does work. Yeah. So anybody who's interested can look at this. And I think
Let
you'll
me show
see
you
actually
from the beginning
Shamash.
what I've written. All right. So if you agree with
Yeah,
this or not. So this is where we started at. We have the north and the east, and then the 20 degrees vector, the average velocity, average speed, I should say actually. And when we get to the acceleration bit right here, and this is the road you were talking about. I tried to make the
yeah.
road you were describing, and this is the calculation of the velocity vector at the end.
Okay, good. So you have made a mistake, and I wonder if anybody wants to Elizabeth. I don't know if you see Shamash's
I
mistake.
don't. Was it in the chat? Is there a link or something? Because I
Oh,
don't see anything.
okay. Yeah, in the chat under Logic Guy there. Sorry, Shamash has an
Yeah,
alter ego
because I need
called
to have my
Logic
phone
Guy.
running and then the other account on the laptop to record.
If you click on that and then don't allow it to use your camera or mic, and then just put some garbage name in, you should bring up in your browser. Oh, if you're on your phone, this might be a little harder though too. I'm on my laptop. Anyway, if anybody wants, oh, Jonathan, let me bring Jonathan up on stage. Maybe Jonathan wants to point out what Shamash has done wrong. I've invited Jonathan. Is he coming up? Okay, Jonathan, I don't know. Maybe you're not coming up. I've invited you a couple times. Just let me know if that's not working. Yeah, so so it'd be better, I guess, if Elizabeth did have access to it, but it's probably pretty difficult. I think on your phone it
No, I
is a
can
little
see
more
it.
difficult. Can you see
Yeah,
it?
yeah, I
Okay.
see that there's like some writing, and you're going up. It says kinematics. It has like the the right side, the B pointing out everything. Yeah, I can see it.
Okay, good. So I guess you have to scroll. Is that right, Shamash? I seem not to be able to scroll myself. At any
Do you
rate,
want me
down
to
at the
go down
bottom
or up?
there,
Do you want me to go
yeah,
down or up?
just show the bottom of the page with the curved
Okay.
road and your velocity addition. Yeah, so you see what we see there is actually it's nice you've got the road, you've got V1 and V2, which are my V initial and V final. The problem is you you basically add v final to v initial, and then you end up with something that you've labeled as v final. So there's clearly something wrong there, right? The final velocity is northward, not angled. So what you actually need to do is add the equation we came to is that the final velocity has to equal the initial velocity plus how much it changed. So I need to basically know that what I want to do is I want to end up with that v final. Yeah, that's good. Draw that. V final is v initial plus delta v. There you go. And now what I want, so if I draw my v initial, I need to add a vector to it such that the result, in other words, from the place I began initially to the place I ended up, is my v final. Okay, so now what you're saying, what you've drawn is v initial. Now, go leave that there for a second. Let me just express in words what that says, and give that thing a name. Call it. Don't call it delta v because it's not. Call it b or something, or v3. There you go. So what that vector diagram shows, this is actually very useful. What the vector diagram that Shamash shows, he starts somewhere, he draws v initial, that takes him to a little place where he then draws v final, starting at the tip of that first vector, and then he draws a third vector from the tip of the second vector back to the starting place. So what that diagram shows is v initial plus v final plus v3 equals 0. That shows me adding 3 vectors and getting a result that has 0 length in no direction, right? I end up right where I started from. I went v initial to the right, and then from there I went v final up, and then from there I went back to the initial starting point. So when I add those 3 vectors, I get 0. That should be kind of a helpful thing. You kind of makes you kind of understand what it means to add vectors. Adding vectors means adding tail to tip, tail to tip, tail to tip, and then finally saying, okay, draw a vector from the initial starting tail to the final tip. And in this case, if I do that, I get 0. So what I actually want is I want to add a vector to v initial such that I end up at a place that gives me v final. V final should be the vector that I get from my initial starting point, the tail of v initial, to the tip of the end. If I add v initial to delta v, I should get v final. Good. Now he's gonna. That's right. So actually, it's not so much that it's wrong. Shamash is saying the diagram he's drawn is wrong. It's not really so much wrong as it is another thing. It's not to the point. But now he's going to draw v initial. So start somewhere, Shamash, and draw v initial. That's right. Yeah. So the vector you draw. So draw v initial. Okay, and then from the tip of v and then let's see what we want to get. We want my final vector, v final, v2 if you want, v final, to be what I get when I go from the tail of v initial up, right? If I draw v final with the same tail, there you go. Now the question is, what vector do I have to add to v initial to get that vector? And what I have to do, right, is I have to draw a vector from the tip of V initial to that place that I want. So now that diagram that he's just drawn shows V initial. I go out to the right, and then I go up and to the left, so that when I add those two vectors, I get V final, which is 40 miles per hour north. Okay, good. So this is, yeah, it is hard. It's interestingly hard to describe this in words in such a way. And the biggest problem is because of that difficulty of getting delta V. But you see then that delta V, in fact, because I've given you such convenient numbers, remember V initial is 30. Just put a 30 there by V initial and a 40 by V final. Then some of you may recognize that what we've just drawn is what's called a 3, 4, 5 right triangle. And if you don't recognize that, you can still use Pythagorean theorem because it is a right triangle. Square 30, square 40, add them up, take the square root, and you get that hypotenuse has a length of 50 miles per hour. So my delta V is a vector that has a magnitude of 50 miles per hour, and its direction, now for this you need a little trigonometry, but I think you can see that vector is closer to north than it is to west, right? If I look at that vector, because V final is bigger than V initial, delta V is closer to north. If I had to pick one of the four directions, I would pick north, but it's clearly westward of north. And if you draw a little perpendicular to the tip of V initial there, draw a little dotted line through the tip of V initial, a vertical dotted line through the tip of V initial. This is so much fun, just directing Shamash to draw these things and then draw that
You're
little
enjoying
angle.
yourself, aren't you?
It's really fun. Draw a little angle thing from the north to the delta V there. Yeah, that one there. Um, you can see he's just drawn another 3, 4, 5 right triangle. That top is also 30. That side is also 40. And you can use a little trigonometry. You can take the arc tangent of 30 over 40 if you want, or the arc sine of 30 over 50, or the arc cosine of 40 over 50. All of those things will tell you that alpha, the angle that he's drawn there, is 37 degrees. So in the end, I find that my delta V vector is 50 miles per hour, 37 degrees west of north. And that's a full and full and complete description of that vector. Right? It tells me how long it is and what direction it is. And then the only thing left to do, if I want to calculate the acceleration, the average acceleration over that 10 seconds, is to divide delta V by 10 seconds. So if you draw delta V vector divided by 10 seconds, yeah, you can see that gives me 5. The 50 divided by the 10 gives me 5. The miles per hour divided by seconds gives me miles per hour per second. So I get, yeah, 5 miles per hour. Oh, no, no, no. Oh, now you're no, and that's not right either, actually. Shamash is ignoring his units here. It was 50 miles per hour divided by 10 seconds. So that gives me 50 miles per
Oh,
hour per second.
wait. Oh, Jesus Christ. Okay, nobody saw this, right? Nobody saw any of it. Forget about it. Okay, what do you want? Do you want just the modulus, right? So I'm not going to confuse everybody. I'm just going to leave the arrows here. I'm going to abuse notation.
Yeah, go ahead and leave it that way, and
Yeah,
then
okay.
just write in 50 miles per hour, 37 degrees north of, so whatever. Yeah, over 10 seconds equals 5. Oh, well, you could do,
Do
don't do that, but no, but don't even do
you
that,
want?
Shamash. I
Yeah,
know you're trying to
you want
convert
this?
units.
Yeah.
I just
What do you
want
want?
those units. I just want exactly what you've got there. It's 50
Okay.
miles per hour per second, right? And per 10 seconds is
Ah,
five.
you want to leave the hour seconds? Okay, okay,
In,
okay.
in, in fact, write it as mph. Write it as mph, not miles per
Okay.
hour.
Yeah, I
Yeah,
like that.
there you go. And then it's, yeah, 5, right? Not 50. Yeah. So the result is 5 miles per hour per second. And that's a weird way usually to express acceleration unless you actually drive a car, because that totally makes sense, right? 5 miles per hour per second generally means your speed is increasing or decreasing or changing in some way by 5 miles per hour every second. That's a completely um, reasonable, kind of understandable thing to talk about. Um, Now, the only thing, of course, is that in that upper equation there, you did leave off directions. You went from a vector equation to a scalar equation.
But I
So
asked
what
for
we really
permission.
no, you did, and I gave you permission. So I'm just now pointing out that if we really wanted to know the acceleration, we'd have to say that it's 5 miles per hour per second, 36, 37 degrees west of north. Right. But it's kind of so it's odd because you might say, well, how is that? How did it get west of north? Well, it became west of north because I had to not only get rid of all of my eastward velocity, but I had to add all that northward velocity so that um, and you notice that if you put that acceleration vector, yeah, just like you're about to do on the road itself, you notice that the acceleration vector is kind of generally toward the inside of the curve. And that's always the case. When you go around a curve, the acceleration vector is always pointing toward the inside of that curve. That's called centripetal acceleration. Okay, I think that's all I really want to do here. I just wanted to kind of experiment with this. I don't know how useful that was. I don't know. Maybe it takes more time to understand some of that, but it's at least a start on the hard part about kinematics is the vector stuff. It's not and the vector stuff really does require a little bit of practice.
Yeah, I was gonna
Let me
say
just
that, John. That was the one
yeah,
thing, like when y'all started this whole kinematics discussion, you, Dr. T. Brown, and Jamal, like a while ago. Besides the fact of the actual terminology, it was just like, okay, so then this can be a vector. Okay, acceleration can be a vector. And this, so you are correct in saying that. Well, obviously you're correct, but I'm just saying that's the part where I get confused the most when
right.
it comes to the vectors because I'm like, so everything can be a vector.
Well, not everything. So things like density, right? Density is not a vector. Time is not a vector, unless well, we don't even want to go there. I mean, you can talk about a direction to time in a sense, but you can just handle that with plus and
But a
minus.
vector, like, I mean, in layman's terms, so the way that I'm trying to understand it, and maybe it's like a little different when it comes specifically to kinematics, but
Right.
maybe this is just relevant to to the displacement vector itself. But basically, it's the vector. It's just describing the position of a point in time. Correct?
Um, well, so a vector is any quantity. For instance, the electric field is a vector, and what that means, and it's a field vector. So what that means is that every point in space has its own electric field, a vector associated with it. So the electric field right here. might be, 100 volts per meter down. That would be a vector, right? So right at some point in space, it might be 100 volts per meter down. It might be that everywhere. If it were that everywhere, then we would say, well, the electric field vector everywhere is 100 volts per meter down. Notice it has a magnitude, the 100 volts per meter. The volts per meter is just the units of electric field as opposed to velocity or something else. And as a direction, down, if you want. So anything that has and for our purposes, a vector really is that. I mean, in more fundamentally, you can talk about directions in, non-spatial kind of arbitrary, abstract mathematical things, but we don't have to go there. I don't think there's anything we ever talk about where a vector, the direction of a vector isn't something that you can characterize with words like north and west and down and up and toward Alpha Centauri or whatever, right? A vector is a vector in the sense that it has a direction in three-dimensional space. There's no need to talk about
Like on a
anything
road,
but
correct?
vectors
Like
like
that's why
that.
you use the road as an example. Like a road, like when we're turning, we're driving our 30 miles east, and then okay, we have to turn north. We have to turn north, so that's why we're essentially going up to the left, essentially, just like the curving road example, correct?
That's right. And so, for instance, I mean, here's an example. If you're on a drag strip, right? So that there's no curve. You're at the start of a drag strip, and the Christmas tree goes down, and you take off in some direction. Then your velocity will be down the drag strip, right? That's the direction. It'll be toward the end of the drag strip. It'll be increasing with time, and so your acceleration will also be toward the end of the drag strip. And then at some point, you pop your parachute. Now your velocity is actually decreasing. And you should be able to use what you've learned now. In fact, maybe this is a good thing to do. Let's suppose you end the drag race. You're at the finish line. You're traveling 300 miles per hour. Let's say east again. So we're traveling 300 miles per hour east. And now you pop the parachute, and after 5 seconds, you're traveling 100 miles per hour east. Can you do that, Shamash? Draw me a 300 mile per hour east, and then down below it a 100 mile per hour east vector.
So first down to the east 300.
Yeah, 300 to the east. And now after a little time, we'll be going 100 miles per hour to the east.
Immediately next to that vector, or just
Yeah,
like
just
next to it?
just show me a vector down below it. Vectors don't have position, so just
Yeah,
draw
but
me a little
okay.
vector down below it.
100
Yeah, no, but to the east.
to the east as well.
Yeah, yeah. So this is a drag car that's going 300 miles per hour, and now it pops its parachute, and a moment later it's going 100 miles per hour. Right? And I want to find out how much did its velocity vector change. And what I want you to do is draw me a vector diagram which shows properly. I think you'll see how the change in the velocity is 200 miles per hour to the west, right? It started 300 miles per hour to the east. It ended up 100 miles per hour to the east. So the change in the velocity was 200 miles per hour to the west. Show me that Show me that vector diagram. Oh, other way around, final minus initial. Okay, so the equation you've drawn there kind of has the problem of mixing scalar kinds of ideas with vector ideas. What I want you to actually show me
Yeah,
is a
but we
vector
can
diagram.
what we can do is, because they are along the same direction, if I put vector I can simplify it all over the place. So we're fine.
Right. Right. You certainly can do that, but But what I want to do is use what we've learned about how vectors work to actually see a vector diagram that shows how v initial plus delta v gives me v final. Okay, right. So you've shown me the three vectors, but now draw a single vector diagram that shows that. Yeah, I think you're doing it. Right. And one should never be afraid when drawing a one-dimensional vector diagram like this to displace the vectors a little bit, right? So they don't have to draw right on top of each other. But that's really good, right? You see how we start somewhere, we go 300 units to the right and then 200 units to the left, and we end up at a place that's 100 units to the right of our starting place. So that represents adding delta V to V initial to get V final. And you can see that the only way to do that is for delta V itself to be to the west. Deceleration is always something that is opposite the direction of the velocity. When I decelerate, that means my acceleration is in the opposite direction of my velocity vector. And you can feel that dynamically. You can feel deceleration because whenever you decelerate, you feel like you're being thrown forward. Whenever you accelerate, you feel like you're being kind of pushed by your seat or being thrown backward or something like that. But that's now getting into dynamics rather than the kinematics is just the description of that stuff. Okay, I think that's maybe this is one of those. This is the time when it's legal to say, "Teacher, my brain is full. Can I be excused?" Um,
Facts.
well, good. I think I'm gonna excuse class for today. This was a good experiment. Makes me happy. I'll just say that. And unless anybody has anything
Someone
else to
put an
say, see
apple
you.
on the teacher's desk.
Yeah. Well, thanks everybody. Class is dismissed. There's the bell. See you later.